epsilon of s equals epsilon with index 1 of s. Then from previous two formulas, 14 and 15, it follows such a bond for the second moment of the process epsilon, formula 16. And that bond does not depend on the, as you can see, on the parameter b1. Next, we repeat the same procedure twice. After making the change of variables a second time in double integral under supremum sign here in the formula 16, we obtain the bond 17, where the notation epsilon 2 of s is used. And after making the same change of variables for the third time, we arrive at the inequality 18. Taking into account the previous notations, epsilon 3 of t, epsilon 2 of t, and epsilon 1 of t, we get such a relation for epsilon 3 of t, that is the product of 8 values of the process epsilon. See also the previous formula 9. And those the expectation in formula 18 that is here has of the form 19. That is the 16th mixed moment of the process epsilon values. Okay. From 18, a rough inequality follows. So it's an inequality 12. Here we just expand the integration region and making in 12 changes of variables t to capital T times T, s to capital T times s, and the same changes of variables for UI variables, we obtain the inequality 21. And let's apply to 21 Hölder's inequality in such of form 3 times. So first with respect to U3 and p equals 2, next with respect u2 and p equals 4, and finally with respect to u1 and p equals 8. In the end, it turns out that the second moment of the process psi 3t has such a upper bound that is given by formula 22. Next, we will sequentially make reverse changes of variables, capital T times T to T, and so on, and receive 23. It is exactly the same inequality that is described in lemma 1, but just for case q equals 3. And so, the question arises how to obtain an inequality 10 similar to 23 for an arbitrary q in n. The expression similar to the first row in the formula 12 is of the form 24. And first of all, we have to represent properly the differences t to the power of q minus s to the power of q and so on. two separate terms containing just powers of t minus s equals u according to our changes of variables, and terms containing both variables u and s. And it will be a generalization of the relation 13. And these differences can be represented of the form, and this will lead to inequality similar to 16, where the coefficient b1 is absent. Then we must take another q minus 1 steps to successfully get rid of the coefficients b2 up to bq. And in final analysis, we will derive the inequality similar to 18, 19, and inequality 23 for general Q to be of the form 10. Okay, let's move on. Step 2. The next step in the proof of theorem 1 is to estimate the right hand side of inequality 10. Here we denote by m with index r and c with index r the moment and the cumulant functions correspondingly of order r of the process epsilon. The explicit expression for cumulants of the stochastic process epsilon is of the form 26. See, for example, the paper on Heide and Leonenko, where dr is the art of the random variable L of 1. From equation 1, taking t equals 1 and according to the condition A, these cumulants can be calculated, and here we given examples of first for cumulants. For example, d1 is equal to 0 according to the condition A, and d2 is a second moment of the random variable L of 1, and so on. Okay, here we introduce the Leonov-Shiraev formula. For more detailed information, see the book Ivanov and Leonenko. Next, we are going to prove lemma 2. So the fulfillment of condition A entails for any q in N the relation 28. That gives us such formula for q epsilon values can be represented as a sum of products of the process epsilon cumulants, which in turn can be divided into 55 sets in accordance with the orders of cumulants in these products. Introduce the notation A for such a supremum of absolute value of this function A hat over all real numbers, and also such a notation for this integral, and here we give a table that contains all these products of cumulants in the first column, and the second column contains the measurements for this integrals of fifth orders that contain these products of cumulants. Also, here there is a continuation of the table, and all the 55 types of cumulants product. Each product of cumulants in each of these 55 sets using condition A can be estimated in a special way. Below we give an example how this should be done. Consider the product of such cumulants C6 times C4 times C3 and times C3, and use the formula 26. Then we can estimate the sixth order cumulant as such a bond for the cumulant C4, and for the first cumulant of the third order we will have such a measurand, and the second cumulant of the third order, so the last one of the given product, can be bounded as it described in formula 29. So here, firstly, under the integral sign, we had a product of three different of three functions had A, where three dots mean some sums of variables from formula 19. And for example, the first one function it can be bounded as A, that is the supremum of the absolute value of this function. In the first and second factors, under the integral sign in 29, the variables from the set T as U1, U2, and U3 do not coincide. Suppose, for example, the first and the second factors are of the form, so that they contains variables, so for example, T and S and the arguments correspondingly. Then, using Fubini's theorem, we can get such a bond 13 for this double integral. And therefore, the fivefold integral in formula 23 corresponding to the given product of cumulants can be bounded by this value that is written down in the 35th row in the table before. Here we give additional examples of some bonds in formula 31, and as I mentioned before, all the bonds are described in this table. Let put d equals maximum value of absolute value of cumulants di, where I belongs to this set for arbitrary q in N. If q equals 3, then d equals the maximum of absolute value of di, where d belongs to this set 2, 3, up to 14 and 16. So here the numbers 1 and 15 are absent because of our condition A, and the cumulant d1 equals 0. Let's majorize in each row of the previous table each value di by d. After this one, can notice that all the estimates on the right side of the table split into 8 types. That is given that are given by formula 32. The terms 32 are present in the estimate of integral in formula 23 with some integer coefficients, and their calculation actually is quite cumbersome. Instead, we are going to write a rougher but manageable bound by counting the total number of terms in formula 27, provided d1 equals 0. Generally speaking, the sum 27 contains BQ terms, so where BQ is the Bell number. That means the number of all possible non-direct partitions of an Q element set. Let be M, where M is greater than or equal to 1, be the Bell numbers, and Sm be the numbers of unordered partitions of the set 1, 2, up to M into subsets that do not contain singletons. Put by definition S0 equals 1, and then the Bell numbers can be represented in such of a form, and from this relation we can find out this recurrence relation that allows us to calculate these SM numbers. So using this relation 33, we write the first 16 numbers SM to reserve the case Q equals 3. Here you can see a table. So the first column is Bell numbers. That is total number of terms after applying the Leonov-Shiraev formula. And the second column contains numbers SM. That is the number of terms without singletons. Those taking into account the above reasoning, we can write the following bond that is given by formula 34. Here, as you can see, S16 is greater than 1 billion, but after taking the eighth root of this value, we approximately have just 13.665. Passing to an arbitrary Q, in N, and subject in formulas 9, 10 to similar processing, we obtain the general rough but observable inequality, proving lemma 2. The inequality number 35. In particular, this equality is correct for case q equals 2, and it will be of the form 36. Okay, let's go on. And the next step 3, the last part of theorem 1 proof is standard. You see, for example, papers Ivanov 2 and Ivanov and Hladun 3. Returning to inequality 35, we take here capital T with index n equals n to the power of alpha, with number alpha greater than 2 to the power of q. Then such a time series of second moments of the process psi q tn converges, and that means that this process tends to zero almost surely, as n tends to infinity. Next, we consider the sequence of random variables zeta n, which is written in the first row in this formula. And after some manipulations, we get such a bond for this sequence. And here we use the notation zeta n1 plus zeta n2. And it is obvious that zeta n1 tends to 0 almost surely, as n tends to infinity. On the other hand, the second moment of the random process zeta n2 has of this form, and can be bounded in such a way.
The series converges less than infinity. The series of expectations is less than infinity.
Yeah, yes, sure, less than infinity. Thank you. So, since according to condition A and formula 27, that is Leonov-Schreiber formula, we can get such a upper bound for the value of the covariance function b of 0, and this series less than infinity, that means that this process tends to 0 almost surely, as n tends to infinity. So, and the theorem 1 is proved.
Viktor, strictly less, not less or equal, strictly less. This line is placed.
Okay, so thank you for useful comment. Let's move on. Here we discuss some statistical application for case q equals 2. An important generalization of classical trigonometric model in statistic of stochastic processes and signal processing is a model of frequency modulated sinusoidal signals observed against a background of random noises having different nature. And the most studied here is the case of linearly frequency modulated signals, which we will refer to as chirp signal. And for one harmonic, it can be written as in formula 37, where A and B are amplitudes, phi is a starting frequency, and psi is a chirp rate. Here you can see the graph of this type of signal for the simplest case, when the signal contains just one harmonic. Suppose we observe a stochastic process 38, where the function g, t, and theta with index 0 has the form 39, where the vector theta 0 is a vector of real values of the parameters of this signal. And here we assume that this sum of sum of squared amplitudes is greater than 0 for each harmonic, and epsilon is a Lévy-driven linear process described in the section 1 of the presentation. For Q equals 2, the uniform strong law of large numbers can be written as in formula 31. And this is the main theorem that allows us to prove the least squares estimate strong consistency of unknown multiple chirp signal parameters for regression model 38.
Viktor, could I ask a question?
Yes,
because, sure. Sorry, my name is Igor Fomenko.
Nice to
I'm
meet you.
just trying to, that very complex filtration problem. We at least what I know, that standard Kolmogorov-Wiener approach for Gaussian using L2 and going through frequency presentation, where we have that famous inequality on information, like integral of minus log or whatever. Do I understand right that for your problem, it's just analog that you're proving, how can I put it, that filtration we can use least squares, or it's because it's we have now kind of not just going from time L2 in time to L2 frequency representation, but where somehow with your that approach with cumulants, we are just working with two spaces, or am I right? Am I wrong? I'm just sorry. I'm just applied in this area mathematician. I'm just trying to understand. And another, so it's in principle noise should be Lévy, and it's your main result. I mean, we cannot estimate without. I mean, let's say here we have just white noise, then it's not good. It's not gonna work, right?
Here we prove strong consistency of least squares estimate, and
Yeah.
just in this case we suppose that the noise is Lévy-driven, as is described before, but also we have the works where the noise is Gaussian.
Okay.
Yeah, we researched two different cases when the Gaussian is weakly and strongly the noise with weak and strong dependence.
Okay. No, I'm just what I know about and what I use as numerical schemes. They're extremely unstable and even for white noise. So I'm just trying to understand your mathematical results. Is it possible somehow to have some real kind of simple examples? Oh, okay, sorry. It just trying to understand.
Okay.
Yeah.
And for Gaussian noise, still you consider least squares estimator, right?
Yes, we consider the least squares estimator, but also we have another works where we consider periodogram type of estimators.
Yeah, because it's kind of, I believe, the main idea of Kolmogorov or whoever was doing it until Kalman filtration, that you can consider least squares in just as maximum likelihood estimator in frequency domain. So it's kind of with chirp signals, it's always a problem. I mean, engineers, they use concept of instantaneous frequency, and nobody knows what is it. It's just a fascinating area itself. And what is important that it's what is the right way even to understand that it's kind of ergodic. T goes to infinity. So if we want some realization, we need probably to consider some big T. And okay, sorry, it's okay.
Okay, so thank you for the question.
And have you compared least squares and periodogram estimators? Which is better?
Yes, actually, for the Gaussian process, we have some results. Actually, we have already proved the asymptotic normality theorems for these estimates, and the final Gaussian distributions has have exactly the same covariance matrices, but the second one, that I mean the case of periodogram time.
Sorry. What is the same covariance matrices? I missed it.
Asymptotic covariance matrix.
Okay.
It
It's the same.
normalizes the estimator and takes a limit.
Yes, but
In distribution.
yes, but in the second case, the periodogram type estimate, we call it periodogram like estimate in our works, has non-zero limit expectation.
So
Limit. Say it, please say it again. It's something important, I believe.
The asymptotic distribution for asymptotic Gaussian distributions for periodogram type estimates has non-zero limit and estimate when
Okay.
tends to infinity.
Therefore, least squares is better. Looks
Yes.
to this regard, least squares is better. If you construct confidence regions, then perhaps they will be smaller for least squares, because for least squares we have centered limit law.
Yes.
Oh, Professor Kukush, could you repeat? It's something. Yeah, I mean, I think.
We have two estimators, least squares and periodogram, and we normalize both estimators in the same way. And take a limit as t tends to infinity. It is limit in distribution, so weak limit. And the limiting process is Gaussian. But for least squares estimator, it is centered. Expectation of limiting process is 0.
Oh, excellent. Okay,
For
so
periodogram, it is non-zero.
yeah, and kind of what Viktor he presented with that. I forgot how proper cumulative that techniques, like I don't know, Shiraev did something many years. It's exactly confirmation through that cumulants. Okay. Sorry, it's difficult for a practitioner to understand the game of different spaces for chirp signals. Okay.
Okay,
And
so
your relation 41 is uniform ergodicity with respect to this B1 and B2. Okay.
Okay, so thank you for comments and answers. Let's continue. Next, we assume that the two values of amplitudes A J0, B J0 for each harmonic are different numbers, and the two values of frequencies phi J0 and psi J0 are different positive numbers, and we arrange the chirp rates, these parameters psi 0 in increasing order, and suppose that the vector of these parameters belongs to such a parametric set, capital psi. In turn, we introduce also the parametric set phi capital, and suppose that the vector of the parameters phi 0 belongs to this set. Next, we consider monotonically, non-decreasing family of open sets psi t that are subsets of this set psi containing vector psi 0 such that the closure of such union these sets psi t over t coincides with closure of this parametric set capital psi with the property B. This property is essential for proving asymptotic properties of the least squares estimates, because it allows us to distinguish different values of these parameters chirp rates, and also it ensures that this product capital T squared times psi 1 tends to plus infinity as T tends to infinity.
Viktor, could you explain? So sorry. So it's kind of it's a family of open sets which non-decreasing, but in limit. So something I'm missing. In limit, it goes to the right value. That's it. Or something I don't understand. What is the big condition with respect to those data sets? So something like
we have open sets and the union is open again. And
yeah,
on the right,
I understand that, but if you consider the intersection, would it be just psi zero? I don't understand.
the closure of the union is just this closed set, which we want.
Yes, and the vector psi 0 belongs to these parametric sets psi t.
Oh, psi t
capital psi t
belongs, but psi t capital is it intersection of those? I mean, open sets or whatever, or it converges. I don't understand the picture.
Let me think.
It looks like you have open ball on the plane,
Right.
of radius 1, and you consider open balls of radius 1 minus 1 over n. And you consider the union of such open balls, and the union will be larger open ball of radius 1. And its closure is the same as the closed ball. Like this.
No, but Professor Kukul, it's also time t capital, which we are making bigger than t0.
Yes, we have continuum such sets.
Okay, so eventually for all t bigger than t0, it would stay in that data set.
We exhaust this larger parametric set by the union of open sets.
Okay. So sorry, Viktor. Yeah, it's just
yes. If I'm not mistaken, this is an approach for the definition of least squares estimators that was proposed by Brillinger a lot of years ago to consider this estimate in such a parametric set because we, after proving some asymptotic properties, we have such relations in a determinator, and we must ensure that these relations tends to plus infinity.
Okay, I simply didn't look carefully at your very first formula.
I explain why we consider such a simplification of the parametric set. The problem is that the trigonometric functions distinguish different parameters in a very bad way. They do not satisfy any regular theorem on consistency of parameters in nonlinear regression. And this condition B, it helps to trigonometric function to distinguish parameter properly to make them consistent. This is the problem.
So it's enormously complex picture, kind of in infinity, we still need separation of all those parameters. And
Absolutely.
It's exactly what for that we have that. Also, yeah, Professor, thanks a lot. Yeah, it's clear now. I am sorry, just it's not exactly my area, but it's fascinating. Okay.
Okay, so let's continue. And here we give the definition of the least squares estimator, and any random vector theta t that is given by formula 42 is such that it is a point of the functional 43 absolute minimum on the parametric set capital theta, where the amplitudes aj and bj can take any values, and the parameters phi and psi take values in this Descartes product of these parametric sets that were introduced in the previous slide, and it is called least squares estimate of the parameter theta 0. And theorem 2 let the conditions A and B be satisfied, then the least squares estimate theta t is a strongly consistent estimate of vector parameter theta 0, in sense that we have such a convergences almost surely as t tends to infinity for each harmonic. And the use of such a strong graph of large numbers 41 leads us to the fact that the proof of theorem 1 does not differ from the proof of theorem 1 in our previous paper, Ivanov and Hladun 3. So here we considered the Gaussian processes, and to obtain the strong consistency for this Lévy-driven process, the obtaining is exactly the same, but we just need to have this strong love of large numbers for this type of random process, and that was described in this presentation. And unfortunately, the asymptotic normality for this kind of process can't be obtained, since a central limit theorem is not available for such a properly normed vector that is the integral from 0 of t, the process epsilon of t that is weighted by the gradient of the function g. Which was proven in work Ivanov, Levon, and Orlovsky only in case q equals 1. And here you can see the references. And if you are interested in the topic, so you can read the full article of these results. The title is On Uniform Strong Graph of Large Numbers for Weighted Lévy-driven Linear Process and Its Application to Statistical Inference, that was published in the journal Theory of Stochastic Processes. So now I have finished my talk. Thank you for your attention. Thank you, organizers, for invitation. And it was a pleasure to take part in this seminar. Thanks.
Please show your references once again.
Yes.
So, statistical inference it is a good journal, statistical inference, and what else? Statistics. It is also a good journal. Yeah. And what is the reason that asymptotic normality works only for q equals 1?
Could you repeat, please?
What happens for q equals 2? So what is the reason that you cannot prove asymptotic normality?
Okay, as I
happens?
mentioned in this slide, we don't have a central limit theorem for such types of integrals. So for case q equals 1, it was proven in the work Ivanov, Leonenko, and Orlovsky. So they used a special approach, and they used the definition of spectral measure of the regression function to prove the asymptotic normality of such an integrals. And as I'm not mistaken, this spectral measure for such a type of regression function does not exist. So we can't use the approach that was described in this article to prove the asymptotic normality property, because we can't prove the central limit theorem.
But you can check by simulation whether the central limit theorem holds for q equals 2. You can
yes,
find
sure,
cover
sure.
probability for normalized integrals and check.
But does spectral measure exist for q equals 2? It's what I don't understand.
No, the spectral measure does not exist for this type of function.
Wait a second. Oh, Whittle estimator for linear random spectrum. I mean, spectral. Here it's spectral density. So it's maybe spectral measure it exists, but it's not absolutely continuous. I mean, okay. I'm just starting.
Maybe some restrictions on this Lévy process is needed to ensure central limit theorem for q equals 2.
Maybe.
Yeah, it's better number 7 to check that it's interesting. It looks Whittle estimator for. Okay.
So here in Appendix B, the central limit theorem is proven for case q equals 1. So if you can check if you want.
Any other questions, remarks?
Victor, I'm just curious because I mean, when I was quite young, I spent some few months to estimating cumulants, but it was some practical problem. How did you do it? Did you use any assistance with I don't know AI, but for your those estimates? You use how I mean it was computationally I mean not computational, what is the right way to say, just analytical estimation. Did you use any help from the computer?
Maple, for example.
Actually, I'm not. I usually don't use any AI
So you
things.
did by
And
hand
yeah,
enumeration, separation, and checking. Okay.
yeah, I just use pen and paper to prove
No,
the
sorry.
theorem. I just use pen and paper.
Okay. Yeah, it's just amazing. But by the way, who is interested in such problems, like if we consider your proof, now there is a wonderful package which I mean not package, AI language which can you can submit your stuff and it would check assumptions and rigorously mathematics behind it. Lean 4. I don't know. I can send a reference because a lot of mathematicians now they use it to verify. That famous mathematician Tao. He is advocated Lean 4. Yeah.
Okay,
Yeah,
thanks. I will check.
And
yeah,
I had
I'll send you because I'm pretty sure that, and it would be great if kind of we just formalize it and put it and Lin4 should work. I mean, why I know it, because I'm in finance, and obviously we have a lot of stupid models, but some models where it requires mathematics, people even they have startups doing it, Lin4 calculation. So it's fascinating. It occurred to me that all the technology with cumulants, Lin4 could be very useful. Okay. But thanks a lot. No. I just understand that it's you need all this old school of analytical schools to document and derive it formula. It's almost like Gauss. He was doing his calculations for least squares.
Yes. Thank you for a very interesting talk with important results. I guess in applications it is interesting. And
yeah, it's. I want to say that it's. It looks like first of all, it's interest in mathematics, right? It's but second, it's I believe that it could give some directions, right, Professor Cooper? I mean, when you explain that with period diagrams, at least it's yeah.
But suppose Q equals 2. You have no asymptotic normality. But how to construct confidence region for your parameters without asymptotic normality?
Actually, the question is open because we don't know the limiting distribution. But if I'm not mistaken, we the limiting distribution will have the covariance limiting covariance matrix of the form as for the Gaussian process. So we can obtain the finite limiting covariance matrix, but we don't know actually the limiting distribution of these estimates.
But you can approximate your estimator by a Gaussian random vector for finite horizon. It could be enough for confidence region.
But maybe it's possible just. It's the whole problem when t goes to infinity. Can we use something like bootstrapping? Just to get like for median, we would use bootstrapping when we have just 9 observations, but or 10, let's say. But here, how we make t quite big enough? It's what I don't understand. Anyway, it's
okay. So then let us thank once again our speaker for
thanks a lot.
Nice results and important models. And next time, Dr. Sergei Shklyar will give a talk. He works at the Geological Institution, and he will speak about some statistical problems arising in geology, perhaps. Okay, so should be interesting. Okay. Professor Maybrother, maybe you want to say something?
Okay, it was very interesting and there were very technical results. It was difficult to understand the proofs, of course, but it seems it is very valuable work. Okay, thank you very much. So let's finish our work, yes?
Yes, yes.
Okay, thank you.
Okay. Thanks. Thank you.
Same.
So thank you for the participants.
Uh-huh.